Hi class, this is section 5.4 Indirect Proofs. We're first going to start off with a warm-up that is just a regular proof like we're used to doing. Given that angle ABC is 104, that angle right here, and angle BCD is 35, we are going to prove that angle BDC is 69, this angle right here. So angle ABC is an exterior angle, angle BCD is an remote interior angle, and the angle that we're looking for is also a remote interior angle. So the first thing we're going to have to use after our given statement is our exterior angle theorem, which says that the exterior angle is the sum of the two remote interior angles. Then we're going to use substitution to plug in the values that we know. And finally subtract to get the measure of the other remote interior angle. So up until now, the proofs we have written have been direct proofs. That means we start with a true hypothesis and end by proving the conclusion is true. An indirect proof, we're going to prove by contradiction. That means we are going to assume that the proof statement is false, then show that that outcome is impossible. This proves the original proof statement is true. So, and whenever we're given a proof statement, we're going to assume that that's false, and then our proof's not going to work out, so then we're going to say, okay, well, then the original one had to be true. So this is called indirect reasoning. In proofs, the steps are to first state the possibilities, assume the opposite of what you want to prove, reason logically to reach a contradiction. The assumption must be false, so whenever you assume the opposite, that's going to turn out being false. Therefore, the original conclusion is true. So your original proof statement will be true and you'll have completed your proof. So the first step is just being able to take proof statements and assume the opposite. So the directions here say state the assumption necessary to start an indirect proof of each proof statement. So if we were given a proof statement that said prove that triangle ABC is not congruent to triangle DEF, to complete an indirect proof, I would have to assume the opposite. So the opposite of that would be that triangle ABC is congruent to triangle DEF. So that's our new proof statement. If we were asked to prove that x is equal to 17, the opposite would be that x is not equal to 17. If we were asked to prove that angle A is an obtuse angle, the opposite would be that angle A is not an obtuse angle. And finally, prove that triangle QRS is isosceles. The opposite would be that triangle QRS is not isosceles. So you're just negating whatever the proof statement is. So for our first proof, we're going to do an algebraic proof because these are easier to see before we get into geometric proofs. So it says write an indirect proof to show that if negative 2x plus 11 is less than 7, then x must be greater than 2. So we're given that negative 2x plus 11 is less than 7, and we are going to prove that x has to be greater than 2. So the first step in our indirect proof is to negate the proof statement. So the opposite of x being greater than 2 would be that x has to be less than or equal to 2. So the opposite of greater than is less than, and then this one is not having it being equal, so we have to show that for the opposite, that it is equal. So we are going to assume that either x is less than 2 or x is equal to 2, and we're going to assume that those are true. Step 2, we're going to make a table with several possibilities for x, assuming that x is less than 2 or that x is 2. So here we have all of our possibilities for x. We have x being equal to 2, and then a bunch of values of x being less than 2. And you take these values and you plug them into negative 2x plus 11, and you get the right-hand side column. So when x is 2, your answer is 7. When x is 1, your answer is 9. When x is 0, it's 11, and so on. So our original proof statement was that we wanted to prove that x has to be greater than 2. Right now we're assuming that if x is less than 2 or equal to 2, that this expression would be less than 7. Here you can see that this expression is either equal to 7 or greater than 7. So when x is less than 2, negative 2x plus 11 is always greater than 7. So here's when x is less than 2, see how it's always greater than 7. And when x is equal to 2, negative 2x plus 11 is equal to 7. In both cases, our assumption, the indirect one right here, leads to a contradiction of the given information that it needs to be less than 7. Therefore, the assumption that x is less than or equal to 2 must be false. So that means the original conclusion that x is greater than 2 has to be true. So since we prove the opposite of this never works, that means that this one has to be true. Let's try another example. What is the correct order of steps for the following indirect proof? So here's our proof. We're given that x plus 5 is greater than 18, and we want to prove that x is greater than 13. You need to list these steps in the correct order. Alright, so your first step would be to assume that x is less than or equal to 13. Then you plug in 13, any of everything that's equal or less than the 13, and you figure out that when x is 13, x plus 5 equals 18, and when x is less than 13, then x plus 5 is less than 18. Then your last step would be number 1. In both cases, the assumption leads to a contradiction. Therefore, the assumption x is less than or equal to 13 is false. So the original conclusion that x is greater than 13 is true. Now, I know that these are algebraic equations or inequalities, and you could just solve them by hand, but this is just an easy way to introduce indirect proofs. So let's look at an example that is using geometry. It's going to be with triangles. Given that triangle ABC is a right triangle with angle C being 90 degrees, we are going to prove that the measure of angle A has to be less than 90 degrees. So we're going to assume that angle A is greater than or equal to 90 degrees for our indirect proof. We know that triangle ABC is a right triangle with angle C being 90. If the measure of angle A was greater than or equal to 90, then triangle ABC would contain more than one angle greater than or equal to 90. But by the triangle sum theorem, a triangle cannot have no more than one angle greater than or equal to 90 degrees. So let's say that C was 90 and angle A was 90. That already equals 180. That's impossible because we still need a measure for angle B. So you can see that it's not working out if angle A was 90 or anything above 90. The conclusion that measure of angle A is greater than or equal to 90 contradicts the given information. Thus, the assumption must be false. Therefore, the measure of angle A is less than 90 is true. That's it for today.